Alright, so in this video, I was going to do a short introduction to what a fault is exactly on a grid, and then we're going to do a little bit of fault analysis practice using the simulation. So we actually going to calculate what the fault will be at probably bus 2, just to understand the concept also, like what exactly going on. So what a fault is, so let's say you had power gen or TGU or one of the power producer entities in Trinidad, and you have a three-phase generator. So it does exactly what it says, right? It produces three-phase power. So basically, the three phases coming out from the plant, you'll have one phase, and another phase coming out. Each of them 120 degrees apart, and the magnitude is based on the voltage magnitude of the site itself, which could change depending on the site. So you have your three phases coming down, and it goes. These lines are very long, like it's very long. And it goes to a bus, and then the bus distributes it to different sites. And just let's say at the end of this long transmission line for each of them, you go into some loads. So there are loads on each of the phases, so they try their best to balance the load on each of the phases. In reality, each phase normally has different loads depending on the time of day and the usage and so on and so forth. But they try their best to keep the phases, the loads on each phase balanced, meaning that everybody using 50 here, 50 here, 50 here. But in reality, it isn't really like that. It might be 20 here, 30 here, because it could change depending on the time of day. And so there's an overly simplified version, but it could get more complex. But for now, generator, three phases of power, and on each phase, you have a different load. Alright, so let's just say on one of the phases, a big tree fall on one of the phases. So let's say the tree fall on this phase, it bursts the line, and now the line, instead of it being connected to here, it bursts. So you have a disconnect. And let's say the line went to ground. So you basically have a short in one of the phases. So this phase, wherever load was on this phase, the load is gone because the load is still there, but you cannot send any power to it because the line went to ground. So this type of fault, when this fault occurs, we as engineers, we will like to know what is the current or the short circuit current that a fault at this position in the line will see. Yeah, so that's basically the premise or the purpose of the course. So we want to know if a fault is to happen on any of these phases, what the fault current will be. And basically the fault current is just the current that will be seen when the fault occurs. So some faults they go to ground, some faults you have a fault from one line to one line. So you have different types of fault, but the fault occurs when you have a disturbance in one of the phases or multiple phases, and we would like to know what is the fault condition. And you have two things you normally calculate for faults. You have the fault current and the MVA fault value. So these are the two things you normally calculate when you're doing fault analysis, right? So our goal is to calculate what the fault current will be. So you have different types of faults. So the two types of faults you will have, so you'll have symmetrical faults and the other one you'll have is asymmetrical faults. So asymmetrical faults, if you're looking at this, diagram, a symmetrical fault is when all three of the phases go to ground or are shorted at the same time, meaning all three go into ground, which is very rare. That doesn't happen all the time. So let's picture a huge tree just fall and burst all three lines coming up. That's very rare. That doesn't happen all the time, right? So that does only happen like 2 to 5% of the time, right? So you call those three-phase balanced faults, meaning all three phases are faulted. Yeah. And then the other ones are asymmetrical, meaning either one of the phases or two of the phases are faulted at the same time. So the two types, so you have a single line to ground, meaning one line goes to ground. The other type, you have a double line to ground, meaning two of the lines go to ground. And the other possibility that could happen is you have a line to line, meaning a tree fell, but instead of bursting the lines, it just connected two lines or shorted two of the lines together, and it creates a line to line fault. Double line is two of the lines going to ground, and the single line is just one line going to ground. And those make up asymmetrical faults. And the symmetrical ones, we have one for now, may have more. But if for this course, you'll have your three-phase balance fault, which means that all three phases are shorted to ground, most of the time, right? So these are the types of faults. A fault is basically any disturbance to your system, right? And you have two types of disturbances, which in terms of faults, symmetrical and asymmetrical faults. So just remember you have a generator. The generator produces three phases. You have a load on each phase. Most of the time the load changes depending on the time of day it is. And based on that, the types of faults that could happen on the lines itself. You have one line going to ground, two lines going to ground, a line shorted to one line, or all three lines going to ground or shorted. And when you're doing fault analysis, the two values you will want to get is if are the fault current at that particular position and the MVA value for the fault. Some things to keep in mind when you're trying to do the calculation. The first thing is the bus or the location. So a bus is basically a point that where the power leaves or a point where the power enters, right? And then the second thing is the voltage at that fault. So the nominal voltage at that position. So you need to know where that is. And the last one is the impedance seen. So the impedance seen is important because if you have a larger impedance seen, you have a smaller fault current. So the smaller, because remember V is equal to IR. So I will equal to V on R. So if you were to decrease R, you'll be increasing your fault current. Yeah? So the further away from the generator you go, the impedance will increase and thus the fault current will decrease. But the closer the fault happens to the generator, the higher the fault current will be. Yeah, because you have less impedance separating the two of them. So normally when you write a fault, you just write a little squiggle and you put F. If it happens at a bus, same thing, you put a little squiggle and you put a F. The F represent the faults. And the steps to know how to draw it, the first thing you start with are your generators. Like normally On top you put a neutral, so a neutral bar, and from your neutral bar you have all your generators, and then from the generators you have your equivalent impedance, meaning the impedance seen from the generation to wherever the fault occurs, and then you have your bus or the location of the fault, and you have that's the squiggle and F. So these really are the steps that you will take when you're drawing the equivalent circuits and stuff, right? So basically that's our introductions to fault and the stuff you had to calculate. So the next video we'll be doing the reduction for this, and you can see and the application of how all these things come together. Alright, so see you in the next one. Adios for now.